So I'm happy
Recovery.
to be here this morning, and I'm just going to sort of give a review of some of the stuff about charged dust mobility on the surface of the moon. I'm going to also talk a little bit about observations on and modeling of dust over the surfaces of asteroids as well, because that sort of ties into the same physics. It's just a different plasma environment and a different gravitational environment there. So this all goes back to the 60s, with observations by Apollo astronauts who, in the orbiter around the moon, were sketching what appeared to be sort of high altitude, thousands of kilometer high altitude streaks that was presumably dust coming off the surface of the moon. And then there were these images from Surveyor landers on the lunar surface in the 60s, prior to the Apollo missions. And this paper analyzing one of those images from Renelson and Criswell in 1974, where this is the image in the paper. And about 10 years ago, I was working on a review article about these processes and trying to understand all this stuff, and did a little bit of investigation into the origins of this picture, because there's a lot of strange things going on in this picture that you can see here from their journal article. The arrow is pointing to some cloud, which is clearly separated from the lunar surface. It also indicates that the caption of the picture says that the picture was taken after sunset, and that circle, if you can see, can you see my mouse pointer?
Yes.
Okay, so the mouse pointer is over a circle that's labeled SD. That's for the solar disk. So that's where the position of the sun was at the time this image was taken. So it's below the horizon. So then you might wonder, well, how can I see the lunar surface if it's nighttime? And so I dug around, and it turns out that this is sort of a pre-Photoshop era Photoshopped picture, where it's a composite of several pictures and things have been rearranged. And the original images look like this. So these are several of the original raw image files from Surveyors 5, 6, and 7, looking toward the horizon after sunset. And the Surveyor 7 images on the right are the ones that Renelson and Criswell were looking at specifically. And here, of course, it's nighttime, so you can't see the lunar surface at all, but the sun is below the horizon. Surveyor 7 had landed inside a crater on the surface of the moon. And so we're looking sort of up at a ridge in the direction of the sun, and we're seeing light. And so that light must be coming from forward scattering from some small particles. So that was the sort of the first indication of something funny going on, or sort of a landmark publication some years after the original measurements. Later in the 70s, Berg et al. Published a summary of all of the observations made by the Apollo 17 lunar ejecta and meteorite instrument, the LEAM instrument, which is this boxy thing that you can see here on the lunar surface. And it had detectors on the top and on two sides facing west and east. And it was intended to measure meteorite impacts and ejecta produced by meteorite impacts. And so the detectors were made to detect very high speed particles, small sort of 1 to 100 micron size particles impacting at least tens of meters per second for ejecta particles, up to many kilometers per second for meteorite impactors. Instead, they saw very different kinds of signals than what they were anticipating, which they interpreted to be larger particles, but slower moving particles. And the figure here is showing the rate of detections as a function of time in the lunar day, where the two vertical lines are indicating sunset on the left and sunrise on the right. and the three different curves are for the three different sensors, and there's some sort of correlation with the sun, sunrise and sunset, which we'll come back to in a second. If we look over the course of many lunations, many lunar days, we can see that that general pattern persists, that there's more of these detections at, in this case, sunrise, but also some at sunset than there are in the middle of the day. That suggests that there's something going on, perhaps with a changing plasma environment that's related to solar illumination on the lunar surface. So all of these things are sort of suggestive that dust is hopping around on the lunar surface and jumping into the LEAM detector and bubbling up like popcorn in a microwave oven for the Surveyor cameras to observe it. And then the Apollo astronauts were saying maybe there's dust even going up many kilometers, even maybe hundreds or thousands of kilometers above the lunar surface. So it sort of is suggestive of this very active dust environment near the surface of the moon. And I was giving a presentation about some of these results many years ago, and David Carrier, who did a lot of important work on analyzing Apollo data, pointed out the following. This is a picture taken by Surveyor III in April 1967 of the place of its foot, basically, of one of its lander feet. And you can see and it bounced. So the spacecraft came down, it hit the moon, and it bounced. And when it bounced, you could see the mark left in the lunar dust by the foot of the Surveyor spacecraft, which had a kind of a textured pattern on the bottom. And Surveyor 3 is important because the Apollo 12 mission then had as one of its objectives to try to land near Surveyor 3. And they did land near Surveyor 3, 100, 150 meters away. And the astronauts went over there and took this picture of that same mark that was left in the lunar surface. Better camera than was on the Surveyor. But you can see that we still see that same textured pattern, subtle pattern in the lunar dust. This was about 2.5 years after the Surveyor landed, so many lunar days later. Just to go back, here you can see in the original Surveyor picture, there's these two little clumps in the center of that footprint that was left there, and you can see that those two clumps here were visible again. So whatever is going on with dust mobility over the lunar surface is just a cautionary tale that it's not what's controlling the appearance of the surface of the moon, the lunar regolith. We're talking about any activity is very limited. It's probably limited to very small particles, 10 microns or so, or smaller. And it's not in large enough amounts such that, for example, here, even after a spacecraft landed and changed the situation of the regolith on the surface of the moon, introducing new shadows, exposing fresh dust to the sun and the plasma environment, and then let 2.5 years go by, it doesn't really look like it has altered that much. So that's a cautionary tale that, you know, we're not talking about giant turnover in terms of mass of dust on the lunar surface. Well, how about those high altitude dust streamers that the Apollo astronauts reported? Stubbs et al. In 2005 proposed a mechanism to electrostatically accelerate grains in the plasma sheath near the lunar surface that could get particles up to that high, called the lunar dust fountain. But subsequent observations and observation campaigns to try to detect these have basically come up empty. The Lunar Reconnaissance Orbiter ultraviolet lamp instrument looked for it, only was able to place an upper limit. The LADEE mission with the LDEX dust detector flew close to the lunar surface, measuring dust, at some altitudes of tens of kilometers, and they detected impact ejecta clouds, which they could link to cometary meteoroid impacts, but not these spontaneous streamers of dust coming off the surface. So what actually is going on? Well, there's a lot of theoretical study of what's the plasma environment there, and I'll get in a few slides, I'll talk about sort of what's the proposed mechanism to explain the observations that we do have that say dust is moving. So we can't disregard those surveyor observations. We can't disregard the LEAM observations. And some of that work said, well, what if the gravitational field is actually very small if you're talking about a very small asteroid? So there was a sort of landmark paper looking at this, Pascal Lee in 1996, who did an analytical study to say, okay, let's estimate what the charge would be on dust particles on the surface of an asteroid. Let's estimate what the electric field strength would be based on sticking an asteroid in the solar wind and exposing it to solar UV. You've got photoelectron current leaving the surface. You've got an ion current to the surface from the solar wind, and an electron current from the solar wind, thermal electron current. You have an electric field near the surface, maybe that can accelerate dust particles away from the surface. And of course, the smaller they are, the easier it is to accelerate them because of the charge to mass ratio going as 1 over the size of the particle. And so what this figure shows is basically his conclusions about what's the largest particle, or actually the largest particle that can be lifted off the surface, which you could turn it around and think of it as what is the smallest particle that could survive on the surface in the face of this electrostatic levitation for different size asteroids, 0.5 kilometer, 5 kilometers, and 50 kilometers. And then, of course, not too much later, we started getting some amazing spacecraft images of the surfaces of small asteroids. Here's Itokawa, that's in that sort of 0.5 kilometer range. There are smooth areas, but for the most part, the surface of the small asteroids looks relatively free of dust. So at a 0th order, sort of to, just looking at the pictures, it's qualitatively consistent with the picture painted by Pascal Lee that small particles may be removed from these particles, and that's not going to happen gravitationally. That's gravity doesn't care about the size. It's going to require non-gravitational force, and electrostatic force is the obvious culprit. And then, of course, the Near Shoemaker spacecraft observed that in many of the craters, and hundreds of the craters on this asteroid, which is in the tens of kilometers in size, that the bottoms of those craters seem to be flat and smooth rather than bowl-shaped. And that was interpreted, they were nicknamed ponds by Robinson, and that was interpreted to be small particles that had, for whatever reason, filled in the bottoms of these craters. So a mechanism was suggested by Robinson in 2004, and then that it was basically the same mechanism that was responsible for the lunar horizon glow seen by the Surveyor images and these LEAM measurements of dust hopping over the surface of the moon. Here are some more of these dust ponds. So in 2004 and 2005 and 2006, I worked on developing, so first we went through and independently cataloged dust ponds ourselves, mapped them out over the surface of the asteroid, and did some straightforward numerical simulations to try to see, well, can that explain the deposit of small particles into these craters? I said 2004 for the Robinson paper. I'm sorry, it was 2002. So I wrote a couple of papers, Colwell 2005 and Houston 2008, where we modeled dust transport due to electrostatic mobilization near the surface of Eros to see what would happen. So the graph here is showing the distribution of ponds as a function of the local surface gravity, because Eros is very oblong, so the areas at the ends of the asteroid have a lower surface gravity than those near the sort of equatorial waist, just because they're twice as far away, basically, from the center of mass of the asteroid. So there's not an even distribution. So we tried to model this. So we did numerical simulations where we calculated the surface potential on the day side, calculate the currents to the dust particle, integrate the equation of motion, and include the effects of topography to some limited extent, which I'll explain in a second, and see where the dust particles go. So these are the equation of motion in the top center, the electric field as a function of the surface potential, phi sub s, the charging equation for the dust particle, and then in the bottom part here, just the 3 different currents to the dust particle, depending on what the potential of the dust particle is, whether it's positive or negative. But you have a solar wind current, you have an electron collection current, and then you have a photo emission current from those. So we just integrate those 2 equations of motion and see where things go. We used initially an analytic solution for the plasma environment near the surface that's indicated by the dashed line. It's from Grard and Tonelli, early work looking at the lunar environment. And the solid line is from a particle and cell simulation that's done by Andrew Poppy, who I believe is speaking to later today, who will probably give a better explanation of this than I'm doing. But it shows reasonably good agreement between the simple analytic solution and what you get from a more detailed computer simulation of that plasma sheath. So that's all just to say that you can come up with a reasonable numerical simulation of the charging and plasma environment near the surface of an asteroid or the moon. And then you can say, all right, let me take a dust particle and start off. Let me just take that dust particle and place it above the lunar surface, in the case that's shown in this slide here, above the lunar surface, let it come to charge equilibrium. So let the currents balance. So I'm magically holding it at a particular height, and find out the ratio of the electric force to the gravitational force experienced by that particle. So what we see is that if we wanted to have a force balance, meaning that the particle is suspended above the lunar surface, that's where Fe equals Fg, and that happens within a few meters of the surface. You can see that we've got these examples here for 0.3 to 2 micron size particles. And for the 2 micron particle, the largest one, the electric force becomes negligible once you're 2 or 3 meters above the surface. You're basically out of the plasma sheath near the lunar surface, which is on the day side. The Debye length is 1 meter or 2, and that's just determined by the photoelectron flux and temperature. So the force balancing is only really going to be possible if you're talking about really tiny particles, submicron particles. And in a lot of the literature initially, that lunar horizon glow was described as levitation of dust. And levitation has a connotation of floating, like you're actually levitating stably. Think about something in a magnetic field, perhaps floating. So the figure here shows the calculated levitation height, and as a function of particle radius, and you can see that we've got 5 microns down up to 40 microns. For the solid curve, there's an unstable lower levitation height, which is only about a meter or so. This is for tiny particles, and in this particular example, I enhanced the photo emission by a factor of 10 to make something happen at all. Well, of course, the dust particles aren't going to be magically just placed above the lunar surface, so we did some simulations where we launched them off the surface. So here you see trajectories of 2 different size particles, 0.21 microns and 0.22 microns, launched vertically off the lunar surface at a speed of 2 meters per second. It's not really a trajectory, it's altitude as a function of time. And then that little green square that just appeared in the lower left corner is where we're going to zoom into for the next slide, which looks like this. So this is what you're seeing here was all taking place in that little lower left corner, the first slide. And the solid black curve shows a ballistic trajectory. So turn off the Lorentz force, forget about charging, forget about the plasma. You launch a particle off the surface of the moon at 2 meters per second. It goes up a meter or so and falls back down 2.5 seconds later. Then if we include the effects of charging, the 0.22 micron size particle gets a little bit of a boost upwards. So it comes down a little bit slower, but it still ends up re-impacting the lunar surface just a few seconds later. The slightly smaller particle, though, just a hair smaller, there's enough of a difference there that that particle is moving slow enough on its way down that it collects enough electrons to be accelerated away from the lunar surface, shows negative potential on the day side. Sorry, I have that backwards. Emits enough photoelectrons to be accelerated away from the positively charged lunar surface on the day side. So it's very, very sensitive to particle size. So we can play around with a lot of those different sorts of simulations and see what things look like. But the bottom line is that if you're talking about trying to get things to sort of stably levitate or do something interesting above the lunar surface, it's a very special range of parameters where anything like that can happen. For the case of the ponds, the so-called dust ponds in the craters of those on the asteroid Eros, the simulation we did, we said as well, if you're moving along over a crater, the crater is shadowed, and so it has a different surface potential. So if the particle is moving over the shadowed surface, we turn off the electric force and the particle can fall into the surface. And that's what you see with the red curve here. So it's just a simple 2-dimensional model of a crater and particles of different sizes following their sort of modified trajectories, and some of them precipitating into craters. So can that actually explain enough dust transport to explain the dust ponds on Eros? Here's a map that shows areas highlighted in red where the sun spends a lot of time near the horizon. And when the sun is near the horizon, you have these strong terminator fields because you have at the terminator a region that's illuminated by the sun. It's got photoelectrons being emitted from the surface adjacent to a nighttime dark surface that does not have that photo emission. And then you can get strong localized electric fields, which potentially you could enhance the mobility of dust at those locations. And the blue diamonds are the locations of the observed ponds on Eros. And you can see that those diamonds are very strongly correlated with the red areas and with low latitudes and a longitude of 0 and 180, which are the areas where the gravitational field on Eros is the smallest. So the other red areas that you see are at a higher gravitational field, a factor of 2, but maybe it's enough to make a difference. So we did simulations of floating dust and let Eros rotate and launched dust particles off the surface and then precipitate into craters or wherever they ended up. And in fact, they did end up landing in craters shown by the sort of heat map that you see here on the right that shows over time, you sort of get a preferential deposition of the particles in a crater. It doesn't really look exactly like those dust ponds. It's not uniformly distributed. It's not in the center of the ponds. And further measurements it's not clear that the size of the particles in the dust ponds are as small as what you get from this levitation. So at the same time that there were these numerical and analytic work being done on this process, a lot of experimental work has been done over the course of the past 20 years. So this is work done by my former graduate student at Colorado, Amanda Sikafus, just to see, okay, can we levitate dust in a plasma sheath? And if I can have the movie cooperate here, you can see here looking into a vacuum chamber, plasma chamber, where she's got some dust particles that set on a pan and just turn on the plasma and it's illuminated by a laser sheet. And sure enough, the dust does levitate. So it is a real process that can happen. And so it's worth considering if that's what's going on to explain some of these phenomena on these objects. But the whole levitation thing seemed to require sort of too much fine tuning of the parameters and also very small particles. So we proposed in our 2008 paper an alternate model that doesn't require levitation. It doesn't require special balance between the electric force and the gravitational force. That was basically just relying on the fact that a crater is a topographic depression. And if you've got dust lifted off the surface at all, where is it likely to end up collecting? And it's just like here in Florida at this time of year is when the leaves have fallen off the trees. And where do the leaves collect? They collect in the corners and in holes and traps behind things. And a crater is like a trap. It's a physical trap for the dust particles. And so we simulated dust hopping and you get a net transport of dust into a topographic low, such as a crater. It doesn't require any special balance or anything like that. It just requires a terminator field, which you have near a crater because it's casting a shadow, and electrostatic launching of the particle off the surface, but not necessarily levitation. So then we come back to the moon, the object of our interest, and those original Surveyor horizon glow images. So those particles are not floating. That would be a much higher cloud and much more extended. And the analysis of those pictures shows that the height of the horizon glow cloud is only about 30 centimeters above the lunar surface. That LEAM instrument, the ejecta meteorite detector, is also about 30 centimeters tall. So those two measurements of dust moving over the lunar surface give a scale height of about 30 centimeters. And if you assume that what you're seeing are just ballistic particles on essentially ballistic trajectories that are only visible because the electrostatic force has launched them off the surface, but is not making any significant modification to their trajectory after they've been launched off the surface, Say, well, how fast they have to be launched off the surface to be going 30 centimeters in height? The answer is about 1 meter per second. And then the question is, well, does dust get knocked off the surface at 1 meter per second? So the experiments that we've been doing at UCF have been impact experiments to look at what that does to knock dust off the surface in a low gravity environment. Most of our experiments have been done in a 0G environment, well, 0G or 1G, but for low speed impacts, nothing much happens at 1G. It's harder to get data at lunar gravity, but we're going to be proposing to do some experiments at lunar gravity, either using suborbital or parabolic airplane flights. And here's an example of some of those experimental data. This is just a, is that not, oh shoot, that was supposed to be a movie, but the movie didn't make it. But this is on a parabolic airplane flight. At the top here, this black thing is a little shooter. At the bottom here is a tray of granular material. For this particular experiment, the plane was flying at 0.05 G parabola. We launched the impactor into it at about 1 meter per second or so, and then we just measure the ejective velocity. We've done this over and over and over again for lots of different impactor speeds and also lots of different types of materials, and to sort of get a relationship between the ejective velocity and the impactor velocity. At the same time, the group in Colorado has continued doing experiments to look at the mobility of dust in increasingly realistic representations of the lunar surface with increasingly realistic representations of the plasma environment there. So this work was done in Colorado. The upper figure shows a spot of dust on a graphite plate. And then the only thing that was done is a plasma was turned on. And after the plasma was turned on, that spot has spread, has become more diffuse. So the dust hopped around, it moved around some. Measurements were made to see sort of what sort of electric fields are produced, horizontal electric fields near the surface. Then additional experiments were done by Xu Wang at Colorado and Mihai Hiranyi and their group. So here you see, again, a before and after view. And this, I believe, is with Martian dust simulant, but the process is the same, where dust was put on an insulating block and adjacent to an insulating block. And then a plasma is turned on and left on for 45 minutes. And then you come back and take a look and see what's happened. And where there is a discontinuity in the plasma, that results in strong enough local electric fields to make that dust move around. So that initial clean pile of dust that you see in the upper right has now been disturbed just by the fact of having a sort of asymmetric plasma environment there. The group at Colorado, this is from, I think, their most recent paper, Carroll et al. 2020. Again, that's from Xu Wang and Mihai Hiranyi's group at University of Colorado, showing here additional experiments where they were able to measure the launch velocity of the particles off the surface. And the scatter plot that you see here in the upper right, there's not a beautiful trend, but the two curves, the blue and the red curve, are based on their analytic model for it. And the data, at least, are sort of falling within those two curves, which represent a range of this gamma parameter. But the important thing is to look at what is the initial launch velocity magnitude. And it's from about 0.2 to about 0.8 meters per second. And this is, I think, remarkable, because a priori, I would have not had any idea what velocity to expect particles undergoing this sort of electrostatic separation from another particle on the lunar surface to be. It could well have been 50 meters per second, for all I would know. But it actually comes in at around a meter per second, which is just exactly what you would expect based on the measurements from the lunar horizon glow seen by Surveyor and from the experiments, from the measurements made by the lunar ejected meteorite experiment, the LEAM data. So how much dust is lofted? The rate of lofting is depends on sort of having a new, fresh surface of your dust. So you sort of turn on the plasma and things jump around. Then the surface redistributes itself to be happy with the plasma environment. And so these results show the rate of dust lofting as a function of time. And it's peaking at 10 to the 4 particles per square centimeter per second, maybe 10 to the 5, 10 to the 6 particles per square centimeter per second. And it depends on the current in the plasma chamber. But you can see that that rate quickly drops down to near zero because the surface sort of arrives at a new equilibrium distribution. And so that suggests that when you first plop down on the surface of the moon, if you're putting a lander on the surface of the moon or something like that, maybe with sensitive optical instruments, you would want to wait a little bit before uncovering the optical elements, because in the initial hour, you've changed the local plasma environment where you have landed on the lunar surface. That may result in an enhanced launching of dust particles off the lunar surface, but that'll settle down over the course of an hour. Alternatively, so you can wait an hour, that's not too long, and then you're probably going to be much safer. And at the same time, since we're not seeing evidence, we don't really have any evidence at all that particles are being launched at speeds greater than about a meter per second. That only goes a fraction of a meter off the surface. So you have a sort of a dirty zone in the first 30 to 50 centimeters above the lunar surface where dust might be moving around from these natural phenomena. And above that, you probably are not going to be getting any significant amounts of electrostatically mobilized dust. So that happily gives a relatively simple mitigation strategy for dealing with this stuff. So I didn't talk at all about Saturn's rings, but since that's what I spent a lot of my work on, that's why that bullet is in this conclusion slide. So the charged dust dynamics is likely going on the surface of the moon. It's likely responsible for horizon glow, and I believe it's maybe responsible for at least some aspects of dust ponds on Eros and removal of small particles from some small asteroids. But I believe that it's primarily a hopping or launching mechanism rather than a floating or levitation mechanism that's going on with these dust particles. And as I was just saying, for future exploration of the lunar surface, the results that we have so far, I think, indicate that this isn't a manageable hazard. Now, there's a completely different set of things you have to deal with if you've got astronauts walking around and they're kicking dust up, and then that dust is electrostatically sticking to equipment or spacesuits and things like that. But if we're just talking about robotic instruments on the surface of the moon or even rovers, if you wait a little bit, the electrostatic mobilization is probably going to settle down. And if you avoid the lowest 30 centimeters above the lunar surface, you're probably not going to have any electrostatic launching that's causing any problems. You would then only need to worry about what are you mechanically kicking up at all. So, of course, we're still sort of in early days of studying this. There have been some, some beautiful experiments done and some numerical simulations, but we don't have a very clear picture about what the potential is like over the surface potential is like over the course of a lunar day at regions, for example, near the pole and near sharp topographic boundaries. So if we're sending things to polar regions, we may find a different sort of environment there. So it would be great to have better measurements of the plasma environment over the course of lunar day from different locations above the lunar surface. The two bullets that I highlighted there in green, I think, are things that we did not really understand very well at all as recently as 5 or 10 years ago, and we have a much better idea of those now, as I described in the last few slides. And I think as we are putting more landers on the surface of the moon, we're going to learn more about whether and to what extent the presence of equipment, astronauts, instrumentation on the surface of the moon may exacerbate this electrostatic launching property. So with that, I'll shut up, and I'd be happy to try to address any questions you may have.
Yeah, thank you, Joshua. Anyone in the audience want to ask Joshua a couple of questions first?
Yeah, hi, this is Sean.
Hello.
Hello, hi. Very nice talk. I never really look into the background about the horizon glow, and that was very nice story you're telling. So that's great.
Thank you.
And so thank you. And since you mentioned Saturn's spokes, I wonder if you would have the time to talk about a few words about how, I mean, there's a theory about the impact plasma as an initiation of that activity. So any new insights on that? Thank you.
Thanks. Sean, are you the Sean Shu that I know?
Yes,
or a different Sean.
Yes,
yeah.
him.
Yeah. Okay. Hi. Yeah. I just see the first name there, so I don't want to make any assumptions. So hi.
Oh, sorry.
Good to hear from you. So yeah, for as you said, one of the early theories for the spokes above Saturn's rings was that they were triggered by impacts, and the impact produces a plasma, and then the idea is that the positive ions produced in that impact event get transported radially outward across the ring by the co-rotational electric field, and that those ions get collected by little tiny particles on the surface of the somewhat larger ring particles and then lift off the surface. There have been some other theories that tried to tie it to electrostatic events in the atmosphere of Sean, of Saturn, and I think that those don't really work out, like in terms of comparing them to the timing of when you see the spokes. I think that they are impact related. And then there are some different variations of the sort of impact model. So Doug Hamilton has a sort of cascading model for the formation of the spokes, where it's not that simple thing that I initially described, which goes back to Greg Morphle and Gertz in the 80s, but something where there's some initial particles that are knocked off, and you get this sort of cascade of ejecta from those things as they move radially outward. I don't, then the reason you see the spokes is because those dust particles, kind of like what I was arguing for the lunar horizon glow, is those particles basically then just follow ballistic trajectories. They're continue on an orbit that's just a slightly inclined orbit around Saturn, and it looks like a spoke just because they all got launched on this radial locus of points above the rings, but they're not following fancy, complicated trajectories or anything like that. And we know that there's a seasonal variation with the spokes, that they only appear close to equinox when the sun is fairly low. And Mihai Hirani, as you probably know, and Colin Mitchell explained that by when the sun is high, the electric field is so strong, those particles just go. So the whatever the triggering mechanism is that causes the particles to get charged, then the electric field is strong enough when the sun is high in the sky that they just leave. So you don't see them. So you don't have, so that launching mechanism of the particles is still there, but they leave the system. So you don't have this collection of dust there. But I don't know of any, I haven't seen any new work in the last several years since the end of the mission. And the mission ended when the sun was high in the sky. And so we haven't really gotten any spoke measurements since like 2012 or so. So it's been a while. I guess the sun is coming back down now. So we may start to see those again with things like Hubble, perhaps.
Well, thanks for that.
So other questions?
Hello. Oh, can you hear me? Yeah.
Yes. Hi.
I'm joining from the NCU. So when you say the dust particles, so do we know, or should we take into account the composition of these dust particles?
Oh, that's a good question. Let me see if I can, I don't know if it's, oopsie, I accidentally ended my slideshow, but what I wanted to do was go back, way back to these charging equations somewhere here. So these charging equations don't really care about the composition. So you get a little bit of the composition of sort of enters into what's the work function of the lunar surface and what's the photoelectron production rate off the lunar surface. So there's some sort of weak dependence on the composition there. But once you take a little tiny particle and put it up, the photoelectron yield is, let's see here, it's going to be wrapped up in this I sub pH 0. I don't think that that's going to be a significant contributor. Like, I don't think you're going to see any real significant difference between sort of like highlands and mare or different regions of the moon based on sort of like a different work function for those particles. And it's only the work function, I think, that would play any role in what these sort of dynamics would be, and the launching and separation of the particles. So that's kind of an educated guess. I haven't studied it in detail, but my gut tells me that the composition would not play a big role.
All right. Any other questions? I thought that Sean would ask the question that because in some experiments you see this kind of supercharging, some dust, small dust getting a very large amount of electron, and then just shoot out, and then there is more
right.
than you have, you have assumed. How would that affect your model?
I'm not sure I understood. If you supercharge a particle?
No, I mean in some of the experiments they use an electron beam or so, a plasma beam irradiating fine dust. They saw some dust could just go out with larger velocities, indicating they have a larger collection of electron charge.
Yeah, well, I would be guessing because I don't really know the details of Sean may know more about it, or maybe Andrew, I see is in the room now, might know more about some of those experiments. For myself, I've been primarily interested in just producing a sort of a photoelectron sheath instead of blasting them with an electron gun. And I don't know the details of experimental results where they've done that and supercharged some of the dust. Supercharge them enough, they'll start breaking apart and things like that. I can't really answer that question very well. I'm sorry.
If I may, I think indeed there was some experiments, or a lot of experiment was done with electron beam with energy of 120 eV. But basically that's simulating the effects of UV ionization, which, because we don't have a proper UV lamp in the lab, and so the kind of, in a way that we are simulating the same ionization process as a particle will be on the airless body surface, that you will have UV ionization and you will be charged in a similar way. So it's not too unrealistic, I would probably end up with that, yeah.
Okay, good. I think that we should have this discussion some other time. Andy, are you ready? Joshua.
Yes.
Thank you so much.
Thank you. My pleasure.
That's very detailed description on the whole thing, and then thank you for going to those old records, to straighten things out. That's very important.
Yeah, my pleasure, and thanks for having me. And it's getting bedtime here on the East Coast, so I'll wish you all a good day there in Taiwan.
Have a good night's sleep.
Yeah, take care. Bye, Sean. Bye, Andrew. Nice to see you briefly. Yeah.
Okay, good night.